welcome back. I hope you had a nice break. Sorry we have to finish the course this way. What I'm going to do, since I have to keep the videos short, is do things faster than I used to. And you can rewind this and pick up the details since it's recorded. We're going to pick up with section 7.2 right now. Please do all of the UCO supplement problems. If you see some of them that are sort of the same, you might say, well, I can do that one already and skip over it. But be able to do those. The remaining test questions will be similar to those kinds of problems that are on the UCO supplement. So beginning with section 7.2 then, I want to refer you back to the textbook here. I'm going to do some of these out of here. What we're going to do is extend what we were doing last time of working with trig identities to derive new trig identities and to simplify expressions, and also we're going to be able to take trig functions of some new angles. There's a total of 6 sum and difference identities. They're a little bit spread out. Here's the first 2. If I have the cosine of the sum of 2 angles, alpha and beta, cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. You can watch this in your textbook. This is straight out of the text. And if you take cosine alpha minus beta, it's cosine alpha cosine beta plus sine alpha sine beta. These come in pairs so that they're easy to remember. The plus goes with the minus and the minus goes with the plus. These can be used to evaluate trig functions of some new angles. The way you usually say these is that cosine of the sum is cosine cosine minus sine sine, and for the difference cosine cosine plus sine sine. So let's try this on the supplement. Suppose I wanted to calculate the cosine of 7 pi over 12. This is the kind of question I like to ask on tests. What is the cosine of 7 pi over 12? We can calculate it using this new identity. In fact, what we can do with these is we can now evaluate exactly any trig function of theta equals a multiple of 15 degrees. Before, all of the angles we could evaluate trig functions of exactly were multiples of 30 or 45. Now we'll be able to do any multiple of 15 degrees. In case you're wondering in radians, that's a multiple of pi over 12. Seven pi over 12 is a multiple of pi over 12, so I know I can do this exactly. The trick is to write these as a sum or difference of special angles. You can do either, and every multiple of 15 degrees works. Well, if I write 7 pi over 12 as 4 pi over 12 plus 3 pi over 12, alright, this is pi over 3 plus pi over 4. I have succeeded in writing the original angle as a sum of 2 special angles, multiples of 30 or 45 degrees. Alright? Now I apply the trig identity. Cosine of the sum is cosine cosine minus sine sine, plus with minus for cosine. This plus generates a minus here. to evaluate these special angles, I can use one of our special triangles. In this triangle, I have sides square root 2 over 2, square root 2 over 2, and 1. So the cosine is the adjacent over hypotenuse is square root 2 over 2. And then in the other special triangle, I'm sorry, this one is for cosine pi over 4. And then also the sine of pi over 4 is opposite over hypotenuse is square root 2 over 2. Now the cosine of pi over 3, I use the other triangle. 1/2. Square root 3 over 2 and 1. Theta here equal pi over 3. So the cosine is the adjacent side over the hypotenuse is 1/2. And the sine is the opposite of the hypotenuse is square root 3 over 2. There is an exact expression for the sine of 7 pi over 12, an angle that we couldn't take the sine and cosine of before. Well, we need to simplify or I'll take points off on the test, right? Top times top is square root 2, bottom is 4, minus square root 3 times square root 2 is square root 6, all over 4. The answer here exactly is square root 2 minus square root 6 all over 4. A lot of the modern calculators can check these angles that are multiples of 15 degrees, and so you can double check this one on your calculator. But there is a new function of the identities for sum and difference of the cosine. Now similarly, we have identities for the sine. If you scroll down in your book, again, I'll leave the proofs of these out because they are not real illustrative, they're long geometry things. They're kind of neat if you know, just to see them, but you don't have to memorize them. If you use geometry again, sine of alpha plus beta turns out to be sine alpha times cosine beta plus cosine alpha times sine beta. Sine of the sum of two angles is sine cosine plus cosine sine. Now plus goes with plus. And sine alpha minus beta is sine cosine minus cosine sine. We can actually prove this one from this one. If you just replace beta with minus beta and using the even and odd identities, you can derive that one directly from this one. So the sum and difference for sine come in pairs too. That can be written succinctly by just changing the signs here. Well, let's take a look at a homework problem for that. Suppose I wanted to calculate now the sine of minus 75 degrees. That's problem C on the supplement. Please try and do all of these. And send me questions by email as you have them. What is the sine of minus 75 degrees? Well, we could write this actually as a sum of two big angles, or a difference of two small negative angles, but what's usually easiest when you have a negative angle is to use the even and odd identities first and rewrite sine of minus 75 degrees as minus the sine of 75 degrees. Sine is odd, so the minus comes out. Now it makes my problem easier because I can get rid of those negative angles. I'll write 75 degrees as 45 degrees plus 30 degrees. now once again for my special triangles, I can evaluate what comes out of the identity. Sine of alpha plus beta is sine cosine plus cosine sine by the identity we just had. And again, referring to our special triangles, I want to draw them again. Sine 45 degrees is square root 2 over 2. Cosine of 30 degrees is square root 3 over 2. Cosine 45 degrees is square root 2 over 2. And sine 30 degrees is a half. That's again out of the special triangles we just had up there. Once again, these will have the same denominator. Square root 2 times square root 3 is square root 6 is all over 4. And square root 2 times 1 is square root 2 all over 4. Same denominator. This comes out to be, distributing the minus square root 6 minus square root 2 all over 4. There exactly is the sine of minus 75 degrees. Doable because 75 degrees is a multiple of 15. Well, finally, there's an identity also for the tangent. I should say a pair of identities. If you scroll down further in the book, you'll see the derivation of it. It's worth looking at it just briefly. If you want to derive the identity for the tangent of the sum of two angles, tangent alpha plus beta, you just use the sine formula and cosine formula, right? Tangent is sine over cosine alpha plus beta. Then sine alpha plus beta is sine cosine plus cosine sine. And cosine is cosine cosine minus sine sine. Those were the sum identities for sine and cosine. Well, if we do some manipulations here, like we did last time in class, simplifying identities, we can reduce this to this expression, which is now tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Evidently, tangent alpha plus beta is tangent plus tangent over 1 minus tangent tangent. We can apply that to find tangent of some new angles now. And then, once we can do sine, cosine, and tangent of sum and difference of two angles, we can do the other three trig functions. There are identities for those too, but they're not worth memorizing because you can do everything with the sine, cosine, and tangent. Alright, so let's look at the next example I have here. Suppose we wanted to evaluate the tangent of 105 degrees. What does that come out to be? Well, we could say that this is tangent of 60 degrees plus 45 degrees, which is then tangent plus tangent over 1 minus tangent tangent. The plus here goes with plus on top and minus on the bottom, and then if you had minus here, you'd put minus on the top and plus on the bottom. So you just, the top one goes with this one, and then the other one's the opposite sign. That's the way you memorize that. But you can memorize the pair at once. Now, again, if we have these special triangles, here's the 60-degree angle, and here's the 45-degree angle. Tangent 45 degrees is opposite over adjacent is 1. Tangent of 60 degrees is opposite over adjacent is square root 3 over 2 over 1/2. 2's both being denominators cancel, and we just get square root 3. So this is square root 3 plus 1 over 1 minus square root 3 times 1. This quotient is 1 plus square root 3 over 1 minus square root 3. And this brings into play some algebra that maybe you haven't used so much in a while. If I just had a square root 3 on the bottom, I could rationalize the denominator, get rid of the radical in the denominator, by multiplying top and bottom by square root 3, but not so when I have 1 minus square root 3. The trick when you have a denominator of the form a plus or minus b square root c is to multiply the numerator and the denominator by its conjugate, a minus or plus b square root c. Plus with minus or minus with plus. Since the denominator here has a minus, I'm going to multiply top and bottom by the conjugate, 1 plus square root 3. And now let's see what that gives us. Bring that up here. Oops. On the top we have to FOIL. 1 times 1 is 1. Then I've got plus square root 3 plus square root 3 is 2 square root 3 from the outside and inside terms. And then plus square root 3 times square root 3 is plus 3. All goes over 1 plus square root 3 on the outside minus square root 3 on the inside. Minus square root 3 times minus square root 3 is minus 3. And you notice when you multiply by the conjugate, the square roots always cancel. That's its purpose. What I have is 4 plus 2 square root 3 on top over 1 minus 3, or minus 2, let's say, on the bottom. But we're not done, right? We can simplify this because there's a common factor of 2. This is twice 2 plus square root 3 over minus 1 times 2. The 2's cancel, and I'm left with minus 2 minus the square root of 3 is the exact value for the tangent of 105 degrees. So on a lot of the problems you have to rationalize the denominator of the form a plus b square root c or a minus square root b square root c by multiplying top and bottom by the conjugate. Well, we also have to be able to simplify expressions. Remember last time when we said each time we get some new identities, we're going to use them to simplify other trigonometric expressions. What if I wanted to rewrite sine of x minus 3 pi over 4? What could I do? Well, it's a sign of a difference. The sine of x minus 3 pi over 4, if you treat x as alpha and 3 pi over 4 as beta, is sine cosine minus cosine sine. And you just put alpha, beta, alpha, beta. Sine and cosine of 3 pi over 4, we know. When, however, you have an angle that's not between 0 and 90 degrees, not acute, we say, then we're going to have to use the unit circle to evaluate the trig functions exactly. So here's 3 pi over 4. A straight angle is pi, so this must be pi over 4. So their sum is pi. When we drop a perpendicular, we say, oh, 45, 45, 90 triangle, I know these sides that fit within the unit circle are square root 2 over 2, square root 2 over 2 and 1, meaning the coordinates are minus square root 2 over 2 since I went left, and plus square root 2 over 2 since I went up. These are the values of cosine and sine of 3 pi over 4. So cosine is the x-coordinate, is minus square root 2 over 2, y-coordinate, plus square root 2 over 2. Evidently, we can rewrite this expression, factoring out the minus square root 2 over 2 from both of these, as minus square root 2 over 2 times sine plus cosine. There's how the sum and difference angles can allow you to rewrite these expressions. Now I want to jump down a little bit here. Another common problem you get is like number 4 here. Suppose that sine A is 2/3 and cosine B is minus 1/4, and that A and B happen to be in the second quadrant here, or maybe along the y-axis, right, between pi over 2 and pi. What is the sine of A plus B, for instance? What is the sine of A plus B? If I only know sine and cosine of two angles, I don't know the angles, except that they're in the second quadrant. Since you have the sign of a sum, you immediately go to the sum identity and say, this is sine cosine plus cosine sine. So the sine sum identity, plus goes with plus. Well, let's see, sine A is 2/3, cosine B is minus 3/4. Cosine A, oh, what's that? Well, you can figure it out from this one. You can use the Pythagorean identities. If we know cosine B, we know immediately that sine B is plus or minus the square root of 1 minus the cosine squared. Remember that one? So this is plus or minus the square root 1 minus, cosine is minus 3/4, so its square is 9/16, plus 9/16, right? And 1 minus 9/16 is with fractions, right? 16/16 minus 9/16 is 7/16. What we have then is plus or minus square root 7 over square root 16, or 4. Is it plus or minus? Well, if it's in quadrant 2, we remember that over in quadrant 2, sine is the x-coordinate, is positive. So this is going to be a plus. And we'll get rid of the minuses and say, oh, it's in quadrant 2. Similarly, we're given sine A and we need cosine A. So we can compute here cosine A is plus or minus square root 1 minus sine squared A. It is plus or minus square root 1 minus 2/3 squared is 4/9. 1 minus 4/9 leaves 5/9. So I've got square root of 5 over 9, or square root of 5/9, or square root of 5 over 3. Is it plus or minus? Well, it's in the second quadrant. In the second quadrant, the x-coordinate cosine, think of this as being on the unit circle, is negative. So this must be minus this time, because of quadrant 2. So I have that the cosine of A is minus square root 5 over 3. of 7 over 4. And so sine, cosine plus cosine sine is, let's see, minus 6/12. When you multiply top times top and get minus 6, bottom times bottom is 12. Plus square root of 5 times square root of 7 minus is minus square root of 35. All over 12. Evidently we have minus 6 minus square root of 35 all over 12 is the sine of A plus B. Well, finally what we can do with these is verify identities. There it is. 3c. Suppose I see this, sine 2x cosine 5x minus sine 5x cosine 2x. How can I simplify that expression? This is the duck rule. If it looks like a duck and it quacks like a duck and it flies like a duck, it must be a duck. And so we say sine cosine minus sine cosine minus sine cosine. That looks almost familiar. If I had sine cosine minus cosine sine, it would work. Well, actually, that's what it is. We have sine 2x to simplify, sine 2x cosine 5x minus sine 5x cosine 2x. We'll just rewrite that and say that's equal to sine cosine minus cosine sine, and if in the identity we were to call this alpha and this beta, this looks just like the trig identity we got, right? Sine alpha cosine beta minus cosine alpha sine beta is a trig identity. This has to be equal to the sine of alpha minus beta according to our formula we memorized. You have to memorize all the trig identities except the ones that will come up in the very last section. These are all very important. They're used extensively in calculus and lots of other subjects later on. So sine alpha minus beta is sine 2x minus 5x, or sine of minus 3x. Typically for an odd function we pull a minus out and rewrite this as minus the sine of plus 3x. There's how that complicated expression simplifies. It's just